Are you online? You know, in my age, it's not good with all these technicalities anymore. But I guess you're there, and most of you have been nice this year. Also very nice. Yeah. Okay. No, you're not. Yeah. But the rest was very good. So I've been asked to give you a very warm welcome for the last Astronomy on Top Bonn of the year. And yeah, these people did good job this year. They did a good job. They had to fight with this COVID virus that also also with us in the factory we had some problems. And they did a good job, and I hope you appreciate that and that you like that. And for this whole event here, we will all be in the background working, or even in front of the camera, or for the chat. You can say hi, interact with the AOT Bonn team in the chat. That would be appreciated. You know, you get one present more if you all interact in this chat with us. We also want to say thank you for all the sponsors that we have. The Tai Chi place here in Bonn, always offering you to make a little bit more workout, also very good for the New Year's resolution. Starting some activities again, not only the couch, bathroom, bed triangle that we all have with the home office these days. And also the SFB 956 Cologne Bonn. Thank you for your good support. For this event, and this is all I want to say to you here in the beginning, I am delighted to tell you that we could convince Britta Schäfer and Dr. Abel Schootemeijer to give us 2 amazing talks about their work. And as you will hear, this is one of the advantages here in the online Zoom, that the Britta is not even here in Germany with us. She's from far away, but stay tuned for more, because I head right over to David Ose to moderate you through this great event.
Thank you very much, Sandra Claus, for this wonderful Christmassy introduction, and a warm welcome to our live stream. Feel warmly reminded for our last chance to participate in the quiz, actually. This is the last quiz we have. About it. Yeah, the stage is yours.
Thank you very much, David. Yeah, I would agree. It's an honor to be invited to an event that is called Astronomy on Tap with such a topic, because yeah, it's quite a small community talking about caring about the upper mesosphere, and yeah, it's in a way between astronomy and meteorology that cares about the lower 10 kilometers of the atmosphere. So, but still, it's a very fascinating thing that I'm happy to talk about today. And yes, I'm sitting in Oslo at the moment, far away from Bonn. But when I studied noctilucent clouds, I did this mostly from Rostock, where I studied, or Bonn, where the Leibniz Institute for Atmospheric Physics is, where I wrote my bachelor's and master's thesis. So what I want to start with, so that we all have a common ground, what this actually is showing a video of noctilucent clouds observed from Warnemünde in 2015. For that, I share another window. Now you should be able to see, yeah, the northern sky observed from a camera installed on the rooftop in Warnemünde. And yeah, this covers some hours in a few seconds now. What is characteristic for these clouds are all these wave structures and bands that you see here now. And the elevation angle is changing throughout the night according to the sun angle. I will come back to that later. Yeah. And let's go back to the presentation. So short about the structure for the talk today. Very first thing, I'm gonna tell you what these noctilucent clouds actually are. Then a short review of observation geometry I already mentioned, and the history since when do we know them, and yeah, then why do they exist? Why is and yeah, very important also, why do we care actually about this region of the atmosphere? Or is that like, it's a quite odd topic compared to meteorology that a lot of more people care about, and astronomy itself. And yeah, well, and the talk with talking more specific about what I actually did work on, and I hope this triggers also questions for you now. Starting with the first question, what are noctilucent clouds? They are ice clouds in 80 to 85 kilometers altitude, and you are able to see them in summer from mid-latitudes and the polar latitudes. So they occur more often the further toward the poles you get. But yeah, due to that you only see them when the sun has set already, you yeah, there's a limit for when you get midnight sun, you won't see them anymore. A fascinating thing about them is that they are really, really small particles. So the ice particles in these clouds have typical diameters of 20 to 70 nanometers, and they are 80 kilometers above the ground. And when you see them, they are several hundred kilometers away. When you see them with bare eyes, and still they make spectacular shows on the night sky. So this is quite fascinating. And yeah, they are showing all these wave structures, which make them scientifically especially interesting. And yeah, they have been observed since 1885. And yeah, this is not just an incident, or like there has been a reason for that, which is a volcano that erupted in 1883, Krakatau, and transported large volumes of both the particulate matter but also water vapor up to higher atmospheric layers. And it took apparently even more time to get that high up, that you get enough water vapor in the mesosphere to form this noctilucent cloud layer. And I called the talk Sky Glows. This is a citation from from one of the first articles that came out about the observations of noctilucent clouds, and I have taken this with me here, and I just want to cite a little bit from that, because it's very very much stating that no one has seen something like that ever before. Ever since the sunsets of 1883 and last year, there has been at times an abnormal glare both before and after sundown. But I've seen nothing in the way of twilight effect so strange as that of Monday evening the 6th, when about 10 p.m. a sea of luminous silvery white cloud lay above a belt of ordinary clear twilight sky, which was rather low in tone and color. These clouds were wave-like in form and evidently at a great elevation, and though they must have received their light from the sun, it was not easy to think so, as upon the dark sky they looked brighter and paler than clouds under a full moon. Yeah, it's just a few more sentences and then it's the full article about like one of the first sightings, and he was not the only one to see that this year, but there was where this was in England, and there were 2 more observations from Germany, one by Backhaus in Kissingen and then by Jesse around Berlin. And Jesse was also one of the guys that became really interested in these new features and continued studying them throughout the next years, and was the earliest to really make serious haze altitude measurements by triangulation, something that I've done with modern digital camera images too. But before going into the actual science, I wanted to shortly give some hand-on tips for you, even if it's the right season in December right now to give that probably. This is a short sketch when you actually are able to see the noctilucent clouds. So you have the sunlight coming in here, and they are still like lighting up this high area of the sky, so you see the NSE, but at lower areas here, you wouldn't. The tropospheric clouds would already be dark. And so the tips for you, if you want to see them yourself, are spend the late summer evening night outside with unobstructed view to the northern sky. Ideally, be in June, July, and the season is in general from mid-May to mid-August. The sun has to be 5 to 15 degrees below the horizon. And there are a couple of events like every year. Of course, you need to have clear sky. They need to be there. So there is a bit of luck involved too. Next, why do they exist and why do we care? So first, why do they exist is and why do they exist in summer? This is because of the reverse temperature cycle compared to the ground in the upper mesosphere. So, and this is true for polar regions especially. This graph is for approximately 69, 70 degrees north. So you see that the temperature curve goes to below 150 Kelvin in summer, while it is much warmer in winter, and you need cold temperatures to form ice, even though there's such little water vapor actually in these high regions of the atmosphere. And now the second part, more like why do we care? An important thing why we care are the structures that we actually see in these clouds. And these wave structures come from gravity wave breaking, and gravity waves are waves that couple the atmosphere by that they are propagating upwards. And characteristic cloud features that you see are summarized here a bit, like you see these large scale bands here, for example, or this is from the night where I also showed the video. Then you have these billow-like structures where you have several parallel lines, and you have these more whirl-like structures that form complete circles too. And this is important for these gravity wave studies are important to get also modeling right and to understand coupling of the atmosphere at all better. And these noctilucent clouds are a unique possibility to study waves and in general this region of the atmosphere, because you get you can see them, you can get backscatter in other measurement instruments that you wouldn't have if there weren't these ice particles. Then it would be much harder to observe what's going on there. And it's in a region, where there's no possibility to send the balloon that high, so you would have to send rockets, and this is only singular measurements done all the time. And last but not least, you also can, since they have been observed since 1885, you have also a pretty long time scale to observe climate trends in the upper atmosphere by looking at intensity and how often the occurrence frequency of these noctilucent clouds. then I come to the part, what did I actually work on?
Yeah, Britta?
I hear that you're asking something, David?
Yeah. Can you hear me?
Yeah, I can.
Okay. I was just wondering about this figure you showed on the slide before. I guess this is very common in meteorology. You see it all day, every day, but this is the first time I see it. So could you explain a bit these
That's true. Yeah, you have the altitude, and like going to where we call it still, it would be atmosphere and not a space already. And this is a temperature profile that you have commonly, like here's the ground. You start at global average would be 15 degrees, and then the temperature is decreasing until the tropopause, until about 10 kilometers, let's say. Then it's stable for a while. Then the warming part is due to ozone and the absorption from that in the stratosphere. And then from the stratopause, that is, you have always, a sphere is one layer, pause is the end of this layer. Then from the stratopause, it's getting colder again. And the large increase in temperature to the thermosphere again is then just because the air is so thin that molecules can move very fast and very far without colliding with any other particles. So from the definition of temperature, you get high speed, so high temperature then. But you wouldn't, it's a different physics than if we would have these high temperatures at higher densities at the ground.
Okay. And the noctilucent clouds are around the mesopause. So.
Yeah, this is where this blue curve has its minimum. This is or slightly below that. So in this, you see my cursor, right? So in this region, where it is, where the cursor is now, you would see noctilucent clouds in summer.
Cool. So right at the edge to open space.
Yeah, and this small line, if we're stopping at this figure anyway, just should show gravity waves that get bigger amplitudes because of air getting thinner when propagating up in the atmosphere, and it's also the mesopause is the region where they to break and where you have energy dissipation and all these nice structures that you see in the clouds. Were there more, or can I go on?
You can go on, thanks.
Okay, yeah, thanks. Yeah, this should be a short summary of what I actually did. I mentioned that Otto Jesse did the first calculations of how high these clouds actually are by triangulation. That means taking camera images or just observations by eye and measuring angles from 2 different sides, or 3 or even more. And of course, they did that with analog pictures or just by angle observations, and the same is possible with digital images today. And this is what I did in my bachelor's, that I took images from Bonn and Warnemünde, so approximately 30 kilometers apart in east-western direction, and observe the same cloud. And then you can take the images by angle calculations, put up a triangle between the spot in the cloud and the 2 observation places, and then calculate where the cloud actually was. And of course, this is not that trivial when you don't know all the angles in your image. So there's actually the spot where I come closest to astronomy, I would say, in this talk. That, how do we know that? We can look at stars and track the stars throughout, like overlay several pictures when we have the NSE just in the lower area of the picture, and then compare from databases where the stars should be and where we see these white dots as a line where the star actually moved, and then we can adjust all our parameters, field of view, elevation, azimuth, and rotation angle, in order to get this right. And then we can go on and find all the cloud altitudes and ideally reconstruct a 3D image of the cloud. That for this. And with another, like when you're not just using the camera images for research, but sending laser beams up into the atmosphere, you can get much more higher resolved information about the layered structure in these clouds. So this is where I've been a lot of times up in northern Norway, where you see by the white star on the map here. This is the island of Andøya in Norway, and there is the Leibniz Institute of Atmospheric Physics in Kulingsborg has an instrument up there, especially for looking at these clouds during the whole summer. They have 24-hour shifts, and you see these green LiDAR beams. LiDAR stands for light detection and ranging. So you send up lasers, and from when they come back, you know from which altitude they came back. And yeah, and the green light is what we have 3 wavelengths there. So this is important for particle size measurements, for example. But for a lot of other studies, the green channel that you also see by eye is the one that is most sensitive to the ice particles and therefore used. This is the building from the outside in the left picture, and during winter. And in the right picture is the open telescope hall, where both the lasers are sent up and we detect the backscatter. And what this looks like then in the end can be for these 3 examples. And you see that in the highest one, you have very short period variations in the noctilucent clouds. So you see all these images are 1 hour time intervals, and just a few kilometers, just the area where we have a noctilucent cloud, so from 81 to 85 kilometers. And then you see in the color code the backscatter. And you see this can be really thin layers with short period variations. This can be thicker layers with more or less, in periods like more homogeneous, and in periods with more backscatter toward the bottom. And in the last example, you see that you really have parallel moving layers for longer times. And what I was doing with these very high resolution things was to make a categorization, so that the idea is that you can get information about the wave properties and about energy dissipation if you can relate this to the certain types of NFC. This has been done for camera pictures before also, like this distinguishing between these bands and billows and just wheels where it's more homogeneous, and the same you can do for the LiDAR, and then couple them with the different types of wave breaking and compare with modeling, which I didn't do myself. And this can give you a lot more information about how energy dissipation works in these regions of the atmosphere. And I'm happy to answer more questions about this and finish with a nice picture from Warnemünde again.
Oh, thank you very much. I was hoping for some pretty pictures, and you showed some. Cool. So your last name is already a hint that you may be a shepherdess of noctilucent clouds in that way. Just a warning, I would like to warn you of a false friend. The gravitational waves and the gravity waves have nothing to do with each other. These are completely different phenomenon. So a question to you is, what actually determines the wavelength of the noctilucent cloud patterns?
That's a good question and kind of complicated. It certainly depends on the mechanism how this wave breaking takes place. So what you see there, there are quite short wavelength of a few kilometers. Let's say between 1 and 5 is quite common. And this is not the wavelength of the gravity waves when they arrive there. This is something that is a secondary wave production in a way when they dissipate there.
Okay, so there are many effects playing into this. Yeah, so there's a lot of science still to be done, I guess. Yeah, I like these noctilucent clouds because they are actually a hint that the Earth might not be flat. Otherwise, we couldn't see them. Yeah, how did you actually come to look into this topic? Have you had some moment when you have seen noctilucent clouds and were wondering about them and then looked for a bachelor thesis?
I haven't actually seen them myself before starting the bachelor thesis. This was just during the process. But yeah, we have at the University of Rostock lectures with people from both the Institute for Oceanography and the Baltic Sea Research in Warnemünde and the ones from the atmospheric site in Kühlungsborn. And yeah, so I attended these lectures and I got interested in the topic before even having seen them myself. And then yeah, I started looking out which bachelor thesis topics there might be at this institute.
Okay, but I guess you have seen many to that time. You mentioned on one slide that there is some relation to climate change, that these noctilucent clouds get more frequent or the other way around. Could you go into detail there?
Yeah, this is what we observe is that they get more frequent, or that the really bright events get more frequent. And there are two reasons that you possibly could think about why they should become brighter. One is it could be colder up there, and one is you could have more water vapor, so that particles can grow bigger. And the second is the larger effect, but both are true for climate change. So while the atmosphere is getting warmer in the lower layers, it's actually getting colder through climate change in the upper mesosphere. But the even more important aspect for them getting brighter is that due to higher methane concentrations in the lower atmosphere and the dissipation processes when being transported up, this actually leads to higher water vapor concentrations up there, and this leads to that the particles can grow bigger and you see brighter noctilucent clouds.
Okay, so we should hope not to see many more noctilucent clouds in the next decades, but still those which we can see should be investigated, and I'm sure you will do this in your PhD thesis. So thank you very much for this talk, and wish you all the best with your research.
Thanks, and thanks for inviting me.
Yeah, you're welcome. So from these very faint and very close objects, these noctilucent clouds, we come to very bright and very distant objects, and Abel Schootemeijer knows everything about these objects. He's from Amsterdam and is doing a postdoc now in Bonn. Actually, he started as a chemist, and now he feels like an astronomer, a real astrophysicist. How did that come?
Hello. Well, I like chemistry also. Well, actually, I like both chemistry and astronomy. But yeah, I have to be a bit careful because some of my chemistry friends might be in the audience here. But in any case, I decided to pursue the astronomy thing because I'm really fascinated by it.
Yeah, so we are very happy to have you in our group. on the same research group as I and the Argelander Institut for Astronomy. And I'm looking forward to the talk. The stage is yours.
Okay, thank you, David. So what I would like to do in this talk is make the night sky a little bit more relatable for you when you are looking at it. So what I would like to cover here is the following things. So very briefly, I would like to discuss what these sources are that we see in the night sky. And the larger part of the talk, I would like to highlight 4 stars that we see in the night sky. These you might have heard of, but maybe you do not know super much about them. These are Betelgeuse, Rigel, Sirius, and Polaris, also known as the polar star. So to start very quickly, what is a star? A star is a sphere of gas that is in equilibrium. We know that stars can live for a very long time, so they're in a stable state. So on one hand, they're more or less in mechanical equilibrium. And that means that while the gravity is pushing inward, there is a gas pressure gradient that is pushing outward. So that is sort of imaged in the picture that I put on the slide. Another way to imagine this is that if there is, for example, a bomb exploding behind me, then I'm pushed forward because the pressure behind me is larger than the pressure in front of me. Okay, so these 2 forces are keeping it in equilibrium, the star. And something else that is going on is that the stars are shining at their surface. So to be in a stable situation, they need an energy source within to keep them to generate the energy that they radiate away. And this is typically the fusion of hydrogen into helium, which liberates some energy and also a little bit of neutrinos. This process is very efficient, so it generates a lot of energy. So the stars do this for the longest amount of time, but at the end of their lives, they can also make heavier elements. So this is a part of the night sky. And what I used for the software that I used for this talk is Stellarium. This is something you can download, but you can also go to the website and explore the night sky yourself. I think it's a really nice piece of software to explore the night sky. So people in the past didn't have Stellarium, but they still looked at the night sky and they used their imaginations on the structures that they saw in the night sky. Let's highlight Orion, for example. It has a characteristic hourglass shape. But what the people in more ancient times thought was that it represented a hunter called Orion. And so Betelgeuse is supposed to be its right shoulder. Rigel is supposed to be its left knee. Here is its belt. If you're looking in very good conditions with very little light pollution, you should also be able to see its sword hanging on its belt. And there's a little bow here. So that's sort of doable. There are also constellations that take a little bit more imagination to see what the people saw who looked at it in ancient times. For example, we have here Ursa Major, which means the big bear, which I'm not able to imagine, but I guess the people in ancient times just had a bigger imagination. Yeah, and it's also known as the Big Dipper. So I promised I wanted to highlight 4 stars. These are 2 in the Orion constellation, Betelgeuse and Rigel. Close to the Orion constellation, I'd also like to highlight Sirius. And maybe you're not able to see this, but at the very top, there is the polar star or the guiding star. And that I will also cover. And I would like to start with the red source here. If you look at it, you can actually see that it's red. And this source is called beetlejuice. Why is it red? I'd like to explain this with the help of this figure. And this figure shows how much energy a source radiates as a function of the wavelength on the x-axis. And the takeaway from this figure is that stars that are hot emit most of their light in the blue. So that's why they look blue. They emit more blue light than red light. For cold sources like betelgeuse that are about 3000 or 4000 Kelvin, it's the other way around. They emit more red light than blue light. And the sun is somewhere in between. It emits about as much blue light as red light, and therefore it looks white. I know we see it as yellow or orange, but that's the atmosphere of the Earth tricking you. In practice, it looks white if you go to space and you do not have to look through the atmosphere anymore. What we also see is that red sources, that cold sources, emit only very little radiation at their surface per square meter. So why is Betelgeuse still a very bright star? The answer is that it can be very bright because it's extremely large. So here's an image of Betelgeuse. The image is taken with long wavelength observations, sub-millimeter observations. And what is shown here is Betelgeuse, and on top of it are on the same scale the objects in the solar system. So the sun in the center and the Earth, which is about 200 times the radius of the sun away from the sun, is much, the distance between Earth and sun is much, much smaller than the star Betelgeuse. So Betelgeuse is so large, it's about 1,000 times the radius of the sun. And because volume goes with the size, with the radius to the power 3, you could fit 1 billion suns into Betelgeuse. And something that makes it special, that it's so large, is that it is one of the few stars that we see not as a point source, but where we can actually look at the surface of it. So that you can see here, that has been resolved in this study and also with the Hubble Space Telescope. And surprisingly, it's not really spherical. It looks a little bit aspherical. Like so the brightest point is not really in the center. It's not perfectly round. So that's something interesting about it. And there is another reason that Betelgeuse is interesting. So about a year ago, it reached the news. So what we see at the right here is the brightness. That's how bright Betelgeuse is to us as a function of time. So we see there is a little bit of variability. Keeps being variable, but at the very end of 2019, it very quickly declined in brightness. And if you look at this graph, you get scared, right? You think that something is about to happen. So many people speculated that the star might explode, which would not have harmed us at Earth, but it would have provided a very spectacular sight in the night sky. It would have been, the brightness of it would have been something in between the brightest star and the moon. So it would have been very, very bright if it had exploded. So the question is, was there a reason to think that Betelgeuse was about to explode, except the sudden dimming? And for that, I would like to take you to the life of a typical massive star. So what I'm going to show here is a 10 solar mass star, so a really massive star. But Betelgeuse is also very massive, even a little bit more massive than 10 solar masses. And what the software that I use for this is called Tulips, and it's developed not by me, but by a colleague of mine in Amsterdam. And the reason she developed this was that she thought that the normal way astronomers show the stars, namely in a Hertzsprung-Russell diagram, is not very relatable. So what they did is, so what she did was, instead of this, the Hertzsprung-Russell diagram that we normally use, is show the star as we would see it, if we were in space at least. So this is the real color of the star at some point in its lifetime. And also this plot shows how big the star is. The only difference between what is in this plot and what we would see in reality is that the star is, that the axes are in the logarithm, because it would not be practical to show it in its real size, because it's very tiny at the beginning relative to the end. Okay, so I'm going to show a movie. This worked when we tested it. Nice, and it still works now. So at the beginning of its life, a star, a 10 solar mass star is relatively small, about 5 times the radius of the sun, and it is hot. So we see it as a blue star. And then here it burns hydrogen. It becomes a little bit larger, a little bit colder, but we still see it as a blue star. Here it has finished burning hydrogen, because all the hydrogen in the center has been converted into helium. Then it very rapidly contracts. It ignites hydrogen in the shell. So look at the timescales. We're at 23.9 million years. And it expands very quickly. So this was just 10,000 years, and it suddenly became much more cold. So here the star roughly have the temperature of the sun, because we would see it in space as a white star. And then the star proceeds to cool down even more, increase in size even more. And after 25 million years, it's near the end of its life, and it would probably explode. But the stellar evolution model was not able to also model the explosion, so it stops after 25.6 million years. But the takeaway is that the star lives as a red supergiant more than 1 million years. So let's say here we're at 24 million years, and then 25.5 million years. So the star burns, so the star is, so this phase is expected to last about 1 million years. So the chance that we would see it explode is rather small. Yeah, and needless to say, it was just a fluctuation in the brightness, and betelgeuse became brighter again. And yeah, it didn't explode yet. Everything went back to normal. And the next star that I would like to talk about is Rigel. So this is at the other side of the hourglass, but it is a blue star. And this is puzzling to us, because I just showed in these models that the stars that are as massive as Betelgeuse and Rigel, which are both about 15 to 20 solar masses, are expected to be either very hot or very cold. But the in-between phase is expected to last only about 10,000 years, which sounds like a lot to us, but is really not much on the lifetime of a star. So there are 2 possibilities. It's coincidence, or the models are wrong. Yeah, and most likely the models are wrong, because that is just something that happens more often than that you see something by coincidence. So the takeaway is that Rigel has a suspicious color. It's blue instead of red, which is strange for us. Okay, the third star is the polar star. I'm afraid that you might not be able to see it because the ID is over it. But this is called the northern star. And if you zoom in a little bit, it is very easy to locate in the sky, because if you take the Big Dipper or the Big Bear, Ursa Major, and you have the right side of the frying pan, and you go up the distance between the top right and the bottom right star 5 times, you end up at the polar star. And this is useful, of course, if you want to navigate. And if you would zoom in even more, you would see that Polaris A has a companion star. We see it as a point source, but there is, but if you zoom in with a telescope, you can see that it has a companion. And if you zoom in even more, you can see that there is a second companion that's even closer. So many of the stars that we are looking at are not, in fact, single stars, but within the source, there are multiple stars that are contributing to the light. And this is an interesting fact, but it really complicates the life of a stellar evolution modeler, such as which is what I do in everyday life. Yeah, and this is what would happen if you take an image of the polar star for a long time. You let the Earth rotate, and then all the other stars smear out, but not so much the polar star, because it's so close. Yeah, because it's almost right above the North Pole. We don't see it move. So that's why we can use it for navigation, because it doesn't move. Okay, and the last star I would like to discuss is Sirius. And Sirius is close to Orion. And this is the perfect time to observe it, because it is in the summer, it is below the horizon permanently. But now it is, you can find it navigating by Orion. So it's a little bit to the left of this constellation. And yeah, as it says, Sirius is the brightest star in the sky. And yeah, why is it so bright? It's not because it is intrinsically very bright. It is bright because it is very close. In comparison with Rigel, it is 100 times closer. So that means that the light of Rigel is 10,000 times more diluted when it reaches our planet, the Earth. Although intrinsically Rigel is much brighter, but just not enough to compensate for its much, much larger distance than the distance of Sirius. Yeah, so something that is close, you also see moving faster, apparently. So imagine that you see someone walking a kilometer away from you. They don't move very quickly through your field of view. But if they're at 10 meters instead of 1 kilometer, and they're walking, they move through your field of view much more quickly. So that is also what we see when you look at Sirius over a longer time scale. And this was already seen about 200 years ago. And Friedrich Bessel in 1844 noticed something else. So not only was it noticed that the star moves in the sky, it was noticed that it moves not in a straight line, but it seems to wobble a little bit when it's moving. I don't know if this works with the camera, but it moves in a line that is not straight. And Friedrich Bessel hypothesized that this is because it is because there is a second companion star that we are not able to see. And we now know that he's right. And the companion star is a very special star. It is called a white dwarf. And a white dwarf is an object that has the mass of the sun, or a mass that's very close to the mass of the sun, but it has the size of the Earth. So because it is so massive, it is able to move, to let Sirius move with the reflex motion. But it is very hard to see because it is such a tiny object that is intrinsically not very luminous. So this explains the situation with Sirius moving not entirely in a straight path. And this white dwarf is the closest white dwarf to Earth that we are aware of. So, yeah, it is time for the final remark. And the final remark is that each star has its own story. And I have told just the story of 4 of these stars. And these 4 stars are Polaris, the guiding star that's always in the north, Betelgeuse, the red giant star that is so big that we can actually look at its surface instead of it just being a point source. And it has this interesting gray dimming event very recently. We have Rigel in the same constellation, but at the other side, that has a color that we do not understand. So whenever I look at it, I think, why is it not red? Why is it blue? We hope to find out more about this in the future. And finally, there I discuss Sirius, which is the brightest star in the sky. And it has a companion that's the closest known white dwarf. Yeah, so, oh yeah, and if you think you will not remember this, I encourage you to press the print screen button, take a screenshot, and look it up for later reference. That was it. Thank you.
Thank you very much, Abel. Oh, we have some. There. Sounds better now. We have a question in the quiz. It's from one of our fans, Boston, and he would like to know, what is the biggest star in the sky?
Apparently, okay, so that can be apparently the biggest star or in reality or the intrinsically biggest star. I assume that the star that is the biggest itself. Betelgeuse, I know, is one of the top contenders because stars do not get much larger than 1,000 times the radius of the sun. They might get a bit bigger, but it is definitely one of the award-winning stars. I do not know by heart which of all the stars in the Milky Way has exactly which size. So I'm quite sure that maybe Antares is a little bit bigger. There might be other stars that are a bit bigger. So Betelgeuse is one of the biggest. I think not the biggest, but I don't know which one is exactly the biggest star.
Okay, thanks. There's another question from Thomas. Does the temperature depend on the size, like some kind of density? So if the size increases, the density of hot molecules decreases.
Typically, stars that are very large have a lower density. This is not true everywhere in the star. Maybe I can go back to the... Maybe I can play the video again. Yeah, so a star gets bigger as it evolves, and that means that the average density in the star decreases. But the density structure also changes. So what happens is that in the core, the density in fact increases by quite a lot. It can increase by 1 or maybe 2 orders of magnitude towards the end of its life, compared to when it starts burning hydrogen. So the answer is that, oh, and the question was also if the temperature depends on the size. Yes. So okay. If a star is a star in the beginning is small and hot, and if the luminosity would stay exactly the same, the temperature is reversely proportional to the radius. I think that it is. The radius is proportional to the temperature squared. Radius is proportional to the temperature to the power -2 if the luminosity stays constant. So the more the star expands, the cooler it gets.
Yeah, I always get confused about this too. Yeah, there are some more interesting questions. but we run out of time a bit, so I hope people can contact you via email, for example, for further discussions. Thank you very much for
Oh
this
yeah, sure. Sorry if I was
tour
a bit too.
through the night sky. And yeah, with this, I would like to remind you that there are some shooting stars to be seen this night. Less than last night, but still many shooting stars to look. And yeah, the final remarks, the solutions of our wonderful quiz will be presented by Sven. So Sven, the microphone is yours.
Yeah, hello, welcome everyone. I hope you can all see and hear me. Yeah, we are going to breeze through the solutions for this month's quiz. Yeah, I hope you all filled in your forms and sent them in, because yeah, now we will present the solutions, so we cannot well, accept any responses anymore. So yeah, let us start with the Astro News. And the first question was, at the beginning of this month, a spacecraft dropped off an asteroid sample on Earth before heading towards further missions. What is the spacecraft's name? And well, the answer for that is it was the Hayabusa 2, which took asteroid samples from the near-Earth asteroid Ryugu. I hope I'm pronouncing these names correctly. And the interesting thing is that it got both surface samples and samples that are deep beneath the surface. Well, the surface samples are kind of obvious how it got that. And the deep surface samples were obtained by basically shooting an explosive charge into the asteroid, then letting it explode and just collecting the debris. So yeah, we now have probes from an asteroid that will be analyzed by the Japanese Space Agency, and we will see what happens there. Okay, the next question was, at the end of last month, ESA signed a contract aiming to clean up space. What is the mission's name? And here the mission's name is Clear Space. Yeah, the proposed concept is that a satellite shoots nets at other satellites and collects them. And once it has collected enough satellites, it basically goes into a very low orbit that everything burns up in the atmosphere. So it's kind of a suicidal space probe that wants to take out other space probes. And yeah, the point why we need this is that there is a lot of space debris in our orbit, and we need to get rid of this, because otherwise very, very unpleasant things might happen that we all want to avoid, including a possible scenario of the destruction of all our satellites. And that would be very, very bad. I hope I don't have to say why. Yeah, then we go to the last question, which is, in zero gravity, not only muscles degrade, the DLR is paying people to stay in bed all day to study the degradation of what? Well, when I first read this article, my reaction was this: there's people getting paid to lie in bed, sign me up. It's actually harder than it sounds, though. You have to stay in bed for an entire month. You have very, very fixed day and night cycles. You're not allowed to take naps. Your food is rationed to the gram of what you eat, so that you keep your weight. So it is to be taken seriously. It's not just chilling in bed for a month. And why are they doing this? They are doing this because they want to study the effect of eyesight. Because in zero gravity, our blood is, well, we have more blood pressure in the brain, basically, because when we have gravity, our blood is pulled towards our feet. So yeah, to simulate this, you would be lying in a bed like this one, and your feet would be pulled up quite a little bit so that your blood really flows to your head, and you have to stay in this pose for 1 month, and you are not allowed to lift both shoulders of the bed. just one shoulder at a time. So you can lie on the side or something, but you cannot sit up. So yeah, it actually sounds very, very unpleasant, and I did not sign up for this. But if you want to, I think they're open till April. So yeah, it might be a quick way to earn some money for if you want to lie in bed for a month. Okay, we are running out of time. I'm sorry. We are moving on to the Pictionary, where we gave you sketches from our talented astronomers, and you had to guess what they are. And the first sketch is, well, of the space probe Chang'e 5, the Chinese space probe that landed on the moon on 1st of December and is supposed to return a sample of the moon, 2 kilograms of moon rocks, actually tomorrow. So stay tuned if everything works out well. Yeah, our next Pictionary is a very, very sad one. It is the Arecibo telescope that is now unfortunately completely destroyed. Will not be used again, and that is a very, very sad loss for science. Yeah, the third and final Pictionary was, to be honest, a bit difficult for people that don't speak German, because this is a kind of a German Pictionary. Namely, it is the Wintersonnenwende, so the winter solstice. Yeah, I apologize for our non-German speaking audience, but I hope that you could solve enough other questions to get the 4 points you need. Okay, we are going to the last category, namely movie posters, where we give you minimalist movie posters and you have to guess which movie it is. And the first one is from a very, very iconic movie from Stanley Kubrick, namely 2001: A Space Odyssey. The second one, also a quite famous movie, which is Back to the Future, an absolute classic, although I have to admit that I have not seen it, so I cannot tell you too much about it. And the third one is maybe the most complicated one, because this is the movie Interstellar, and the minimalist movie poster is basically hinting towards the weird behavior of time in this movie. Yeah, that was our quiz for this month. Yeah, we hope you had fun. We hope to see you again next month. Some of you might win some prizes by participating. You need to have more than half of the answers right, and you have to be lucky enough to be one of the 3 randomly drawn winners. If you have that, then we can contact you via email and offer you one of our prizes. You can win this time 2 books: The Indisputable Existence of Santa Claus and Die Physik des Unmöglichen. So 1 English and 1 German book. You can win a metal building kit of the Space Shuttle Discovery. You can win an insulated coffee mug with our wonderful logo on it. And you can win Tai Chi vouchers for Bonn. So a little disclaimer, don't choose these vouchers when you don't live in Bonn, because you can only apply them here. Yeah, with that, I am done. I thank you all for the attention and for participating, and I hope to see you all next month. Have a nice Christmas, and yeah, get good into the next year.
Thank you, Sven, very much for presenting the quiz, as always. And I want to conclude this event today, which was approximately an hour. And I want to thank you, Britta, thank you, Abel, for giving these awesome talks. Both of them were mind-blowing. I love all astronomy topics, so I'm biased, but thank you wholeheartedly from me and from the whole team. Thank you, Laila, for doing all the technical stuff as always. Thank you, David, for your awesome moderation, but also thank you, Manali, for doing the chat, for Anna for doing the Twitter account, and for everyone else who helped. the whole year to get this done. I hope you all stay true to us also in 2021, and we will kick off the year with a slightly different format than usual. We will have panel discussions where we have different concept of science, or maybe not science, you know, going in the fiction direction. And then you actually have to vote which is which. And we hope that this will be an entertaining alternative concept for once. And then in February, we will also be back with some more amazing talks. So stay tuned. I wish you a Merry Christmas and happy